Hello everyone. I want to take a look at a couple more examples where we're working with vectors in the coordinate plane. Specifically, I have two concepts to take a look at here. The first one is we're going to be finding the component form of a vector. We've already talked about that when we know the initial point and we know the terminal point of the vector. However, sometimes we're given different information, and we still want to be able to find the component form. The reason we want the component form is because it makes it easier to combine vectors together. Let's say you want to find the resultant vector. If we know the component form, it's as simple as adding the x's and adding the y's. So if I can go from knowing the magnitude and the direction, and I can write this in the component form, it might make those things easier. Okay. The second concept is finding the direction of a vector. Again, sometimes that's useful so that we can work with it from there. Okay, so let's start off here. Find the component form of vector v with magnitude 8 and direction 210. So let's just sketch this out so we can think about it a little bit. So nothing fancy, just a real simple sketch. So a direction of 210 starting from the positive y-axis. So then rotated 210 degrees. So that's 180, and then another 30. Puts the vector something like this. So then this angle, that is 210. Okay? And then the other thing we know is that the magnitude is 8. So the length of this vector is 8. Okay. Now the component form of a vector, remember that tells us the change in x and the change in y. It tells us how far left or right it has to go, and how far up or down. So if I draw in this right triangle, we need to figure out what that length is there, the change in x, and we need to figure out this length here, the change in y. So this is, we used a and b before. Okay. Now, as you can see, drawing that out, we end up with a triangle. Lucky for us, we have lots of tools that we can use with triangles. For example, we have trigonometry at our disposal. Inside this triangle, I know that this angle is 30, and I know that the hypotenuse is 8. Given that information, I can find the two legs of this triangle. Okay. However, we can actually simplify that even further. Because we know the angle of 2 is 210, when I use sine and cosine to find these two side lengths, the sine of 210 and the cosine of 210, it knows what quadrant this vector is going to end up in. So the component form for vector v, we can simplify that and we can make this pretty general. So if you think about this, so if I want to find my change in a, that's the adjacent side. I know the hypotenuse, so I would end up using cosine. So then the cosine of this angle is equal to adjacent over hypotenuse. So I would multiply both sides by 8, and that would give me that length. But let's keep it general first. So 8, that was the magnitude of this vector. So the magnitude of the vector times the cosine of the angle, that's going to give me my change in x. And following the exact same argument for the change in y, we would do the magnitude of the vector times the sine of theta. So b, this is the opposite side, hypotenuse, and again you'd multiply by 8 to get that length. So let's see, so we have 8 times the cosine of 210 and 8 times the sine of 210. Helps if I write that in there. Okay, 210 is on the unit circle. So the cosine of 210, that's negative square root of 3 over 2. And the sine of 210 is negative 1/2. And then simplifying that out, so our component form for our vector v So 8 divided by 2, so this is negative 4 square roots of 3 and negative 4. And there's the component form. And like I said, now that we know that, if I wanted to add it to another vector, I could easily do it. That just gives us a lot of information. Okay, now let's kind of go the other direction, the other way, and find the direction of a vector. Again, let's start off just by sketching it out and thinking about it a little bit. So negative 3, negative 8. So this is A and B. So negative 3 in the x direction, negative 8 in the y direction. So maybe we're down here somewhere. Not exact, just trying to get an idea. And again, if I draw in the triangle here, so we're going negative 3 in the x direction, negative 8 in the y direction. As a triangle, maybe those would be positive, but we want the direction. So we want to find this angle, right? Starting from x and then rotated to where this vector is. Okay. Now I do have a triangle. So that means, again, I can use trig to find these angles. So I know these two sides, I could find the magnitude, but let's find the angle that's on the inside here. And then what we can do is, if I can find the angle on the inside, I can just add the 180, and that's my direction. So just in general, the tangent of theta, putting this in a general form just with that reasoning, this would be b over a, right? The opposite side divided by the adjacent side. So our angle, the tangent, is equal to the opposite side over the adjacent side. Another way you could think about that, how we looked up here in terms of sine and cosine, this is the magnitude of the vector times the sine, right? That's our vertical change. And our horizontal change, it's like this. This general form is always going to work. The only thing that we need to be careful of is once we get to the angles that are bigger than 180, the ones that are down here in quadrants 3 and quadrant 4, we may need to work with it a little bit so we end up with the correct answer. So for example, for us, if I plug in b and a, we get the tangent of theta is equal to negative 8 over negative 3. Now those negatives are going to cancel out. So this is the same as the tangent of theta is equal to 8/3. Now if I type this into my calculator, if I do the inverse tangent to solve this, because those negatives canceled out, and because it's just the way that we normally define tangent here, the angle I'm going to get is actually going to be the one that's in quadrant 1, right? Because of the symmetry on the unit circle, there's a second angle that's going to give us the same value of tangent. So negative 3, negative 8, that's the same as 3 and up 8. So if I type that in, the inverse tangent of 8 divided by 3, the angle I end up with, I get 69.4, which would be the angle going this way. However, that's not the one we want, right? We want the angle that's over here in quadrant 3. So because I know the location of my vector, I know that I need to change this to get the correct angle. So to do that, we'll just add on 180. Right, so this gives me the angle that's over here. I need to get to the other side, so adding on 180. So our angle, our direction, is about 249.4. And that angle makes much more sense. All right, so there we go. 2 more examples, 2 useful things to be able to do with vectors in the coordinate plane.